Very good morning, my dear friends. A hearty welcome to my YouTube channel. Myself, Dr. M. H. Channaya. And friends, in today's video, we will work out a problem on the application of a curved beam, wherein you have a circular ring which is open and it is of circular cross section and it has been subjected to a load of 25 kilonewton. This P is 25 kilonewton, and we have been asked to determine what are the values at the extreme fibers of the critical section. Friends, if you just see the diagram here, when this ring is subjected to a compressive load P, what happens? The inner fibers at B gets contracted, whereas the fibers at A, that is at the outer fiber A, it gets elongated. And friends, we will analyze each of these points separately and see what are the stresses. Friends, you know very well, this is subjected to two types of stresses. One is the stress due to that load, which is called the direct stress, that is given by the formula direct stress sigma D is equal to the load divided by area of cross section. Is a fundamental concept. You know the load, the cross section is given to us, that is circular cross section. The area is pi d square by 4, and hence you will be able to calculate what is the value of the direct stress. And friends, remember, because of this load P, the critical cross section AB is subjected to the direct load, which is compressive in nature. So friends, and then when you come to this eccentricity, when you see the center of curvature here, friends, we have to find out what are the stresses. Number one is the direct stress. The second is the secondary stress. Friends, here what happens, friends, because of this distance between center of curvature and centroid of the figure, we have a bending stress. So there are two types of bending stress. The normal stress due to bending at the inner fiber, which is called as sigma Bi, and the normal stress due to bending at the outer fiber, that is at A, that we called as sigma B at A. So friends, to say totally, the cross section AB is subjected to the combined effect of the direct stress and the normal stress due to bending. So friends, we will take up each of these separately, point A and B separately, and find out what is the value of stress at the extreme fibers A and B. Friends, if you consider point A, point A is the outer fiber. I will say here outer fiber. Friends, we have this sigma O, the total stress at A at the outer fiber is given by sigma direct plus sigma B naught. Stress at the, that's a normal stress due to bending at the outer fiber. Friends, I told you the sigma direct is minus P by A, because the whole cross section is subjected to a compressive stress, plus sigma B naught. Friends, look at the board carefully. When you subject it to this load, the outer fiber is elongated. So sigma B naught will be mb times C naught divided by A E R naught. Friends, this equation is available in machine design data handbook, authored by any author for that matter. Friends, here we need to calculate what are these area, eccentricity, MB, C naught, etc. And friends, now let us find out all these parameters connected with the cross section. So friends, I will just write down the elongated or the enlarged cross section AB, the enlarged cross section of that AB. This is A and this is B. You have the center of curvature somewhere here. V is called as C. Friends, this is the cross section AB and this center of curvature. And let us see what are these parameters. Friends, the distance between C and the inner fiber is called Ri. And this Ri value is given in the question as 60 radius. So this is 60 mm. Friend, on the same line, the distance from center of curvature to the external fiber, extreme outer fiber is this much. This is 60 and the cross section is 100 mm dia. So friends, this will become R0. R0 is the distance from A to the center of curvature. This will be very obviously equal to 60 plus 100. So R0 is equal to 100 millimeter. Then friends, this is the centroidal axis, which I call it as say O. And this distance is called as RC. RC is the distance between the centroidal axis and the center of curvature C. Friends, if you see the diagram, particularly in case of triangular, square and circular cross section, C exactly lies at the center of the cross section. So this RC will be Ri plus D by 2. So this is Ri is 60, D by 2 is 50. That is equal to 110 millimeter. Then friends, we have a term or an axis called the neutral axis, which does not undergo either tension or compression. I will call this as N and N. It's a neutral axis. And the distance from here to here, center of curvature to the neutral axis, is called Rn. Friends, this Rn is obtained from the machine design data handbook, and there is a table which will give you the value of Rn for all types of cross sections used in the curved beams. And I have told you in one of the previous videos, the various cross sections are circular, rectangular, then we have trapezoidal, which is the most common type of cross section used in crane hooks curved beam. Then we have the I section and the T section. Now friends, after getting all this, let us find out what is Rn. Friends, Rn is the distance of the neutral axis from C, from here to here. Friends, that will be something like Ra plus this gap. And there is a formula in the handbook. It says Rn is equal to root Ri plus root R0 whole square divided by 4. Friends, we know Ri 60, R0 160. If you simplify this, friends, this Rn works out to 103.99 mm. This is a very important calculation because all other values depend on this Rn. So we have got the value of Rn. Then friends, there are terms required in the expression like CIE. CI, friends, is the distance between the neutral axis and the inner fiber. Between neutral axis and the inner fiber is called CI. So friends, this CI from the diagram is Rn minus Ri. From this Rn, if you subtract Ri, you will get Ci. Ci is Rn minus Ri. Rn is 103.99 and Ri is equal to 60, and you get this as 43.99 millimeter. We have the CI we calculated. And then friends, the distance between Ci to the external fiber is called C naught. Friends, this C naught very obviously can be obtained from this diameter. So diameter D minus Ci will give you C naught. So I will say C naught is equal to D minus Ci. D is 100 and Ci value is 43.99, and friends, you will get this value C naught is equal to 56.01 millimeter. Then friends, you have a term called eccentricity. Eccentricity is given by the formula E is equal to RC minus Rn. So this RC value you know, Rn value you know. RC value is 110 minus Rn is 103.99, and you get a value equal to 6.01 mm. Friends, remember, in all the problems, irrespective of the cross section of the curved beam, this value of RC is always greater than Rn. So you should be very careful while calculating the values of RC and Rn. So this RC should always be greater than Rn. This point you should keep in your mind. Friends, you have calculated all the parameters required to compute the stresses at the extreme fibers. So friends, now I will take the outer fiber, that is sigma O, that is stress at the outer fiber. So that is at A is equal to sigma direct plus sigma bending at the outer fiber. And this can be rewritten as sigma D is minus P by A because the load is compressive, plus sigma B naught at the outer fiber, the fibers undergo tension or extension. This is plus MB C naught divided by A E R naught. This is the formula. So if you are able to substitute these values, you will get the answer. So that is friends, P is given to be 25 kilonewton, that I am going to convert it to Newton multiplying by 10 to the power of 3. Area of cross section is the area of cross section of the circular beam, that is pi by 4 d square. D is 100 and square of this plus MB. Friends, MB is given by the formula P into RC. So this is to be remembered by you in this chapter. P is 25 kilonewton into 10 to the power of 3 Newton. RC value is equal to 110. So you have the value of this MB. You can simplify and put the value. Friends, then you have this C naught. C naught is equal to 56.01 multiplied by 56.01 multiplied by C naught. We have already done it. MB C naught divided by area pi by 400 square multiplied by eccentricity 6.01 mm. R naught is 160. Friends, if you simplify this at the extreme fiber O of the curved beam, you get the value at outer fiber as 17.2144. 17.2144. So in Newton per mm square. Friends, you see at the outer fiber, since the fibers undergo elongation, you get a positive value of this sigma O at the outer fiber. Friends, on the same lines, let us find out what is the magnitude of stress at the inner fiber. So friends, the inner fiber is B. So I will say sigma I at B. The regular formula is P by A with a negative sign minus MB CI divided by AER, because we are taking the inner fiber, all this should be with respect to the inner fiber. Friends, here I have written minus MB because I told you in one of my previous videos, if this MB is positive at one of the fibers, it will be negative at the other fiber. So friends, this value will just substitute. P is minus 25 into 10 to the power of 3. This is compression throughout by pi by 4 d square. That is 100 square. Is the value of this P by A, the direct stress, plus MB, I think I told you already, it is P into RC. P is 25 into 10 to the power of 3. RC value is 110, we have calculated. CI value is, friends, 43.99. 43.99 divided by area, again pi by 4, 100 square, diameter square, multiplied by eccentricity 6.01, and this value of Ri is 60 millimeter. Friends, if you simplify this, friends, you get this value as minus 45.8972 minus 45.8972 Newton per mm square. Friends, we are able to calculate the extreme fiber stresses, that is the addition of the direct stress and the secondary stress, and the value works out to minus 45.8972. And friends, remember this important concept that in any curved beam, whether it is subjected to a pull or to a compression, if one of the stresses at the extreme fiber is positive, the other will be negative. For example, in this case, the stress at the inner fiber is negative, and very obviously, the stress at the outer fiber should be positive, and we got a value sigma O at A, the external fiber, as 17.2144. This is the value we got. So friends, this is how we work out the problem on the curved beams. And friends, you please go through the other video on the same circular cross section, which is subjected to a tensile load instead of a compressive load. And please make a comparison of that video with this video, and you will be able to get clear concept of the fiber stresses, that is the extreme fiber stresses. Friends, I hope the presentation was interesting, and if you like this video, please pass another, send this information to all your friends. Have always the concept of sharing with your friends. Friends, thank you very much for watching my YouTube video. Have a wonderful Sunday.